Good afternoon, everyone. Speaking to the podium.
Yeah, because the mic is in there.
Okay. Good afternoon, everyone. Welcome to Living Walls for the New York City subway system. I'm Adam Tarakan. This is Kelly Okanomu. Our advisor for this project was Dr. Beth Wittig. We've all smelled the noxious subway air while waiting for the train, cringed at the moldy beams, and sweltered underground in the summer heat. Air quality, comfort, beautification. These are the issues we are addressing by creating a living wall system for the New York City subway. The major problem in the New York City subway system is the air quality, specifically high concentrations of particulate matter. Airborne particulate matter, PM, also known as particle pollution, is a mixture of solid particles and liquid droplets found in the air, including acids, metals, soils, and dust particles. Sources can be natural or anthropogenic, such as from forest fires and the combustion of fossil fuels. Particles less than 2.5 micrometers in diameter are the most dangerous and are mostly comprised of combustion products. They easily penetrate the lungs, causing inflammation. Adverse health effects include asthma, lung cancer, respiratory disease, birth defects, and premature death. In fact, air pollution is responsible for 2.1 million deaths a year.
Particulate matter concentrations measured in subway stations during morning and evening rush hours were generally 2 to 7 times the EPA 24-hour ambient air standard of 35 micrograms per cubic meter. Sources of particulate matter in the subway can be divided into 2 categories. First are the ones generated within the subway, such as they're coming from interaction of a train's electrical shoe with the supply rail, friction from brakes, or a diesel-powered maintenance machinery operation. And then we have particulate matter intruding from ambient air, which is coming from traffic emissions, wear vehicle components, and suspension of road dust. Ventilation also greatly affects air quality. Ventilation in the subway is achieved through grates and access points, and only a few newer stations in New York City have what is known as air tempering, which is mechanical ventilation. Air movements on the platform are influenced by draft and the piston effect of trains moving through the tunnels. I think we had a video here that is not showing up, illustrating what the piston effect looks like. Particulate matter concentrations and elemental compositions vary greatly among stations and cities, and some of the factors that affect that are station depth and volume, station width and tunnel configuration, the age of the station, mechanical ventilation, and others. Through studies, it's been discovered that considerable lateral variation is observed on the platform, but greater accumulation of particulates occurs at one end of the platform, and that's the train entry point.
Okay,
Yeah, but I think it's,
too late.
yeah. Sorry, the computer froze. Okay, we're good. Sorry. Sorry, guys.
The second problem we're addressing is comfort in the New York City subway. We all know how hot it gets, how stuffy the humidity feels, and how unbearable the odors can be. Here you can see in the photo how ugly some of the stations look when poorly maintained or when lacking art or greenery. By addressing air quality, comfort, and beautification, we aim to improve the overall health of commuters and MTA employees. A study conducted in Denmark between the years of 1985 to 2003 monitored over 900,000 Danish residents from their birth to the age of 10. They evaluated each individual's proximity to green space and correlated this relationship with their mental health. Children that grew up around high levels of green space were at a lower risk of developing psychiatric disorders as adolescents and adults. Children who grew up around the lowest levels of green space had as high as a 15 to 55% chance of developing a psychiatric disorder such as depression, anxiety, and substance abuse later in life. Schizophrenic risk is 200% higher for children who grew up in the most densely urbanized areas. Based on this long-term study, you can see the importance of increasing green space in densely urban areas.
So our solution is green walls. Green walls consist of living plants that need to be supported in a hospitable environment. And we see our living wall system helping with these three things that we talked about before, starting with air quality. Plants through phytoremediation can sequester particulate matter when particulate matter deposits on the leaves, and with mechanical devices accelerating pollutant diffusion onto the plant substrates. Moving on to comfort, plants can remove CO2, which can help modulate interior temperature and humidity levels. And also plants can lower interior temperatures through evapotranspiration. Lastly, we think a green wall will help keep the subway cleaner because particulates will be accumulated on the leaves instead of subway surfaces, and will visually improve the platform.
Here are 3 precedents which help inspire our design. Figure 8 shows a subterranean vegetable farm which grows lettuce using LED lights grown in hydroponic pots. In figure 9, you can see an actual living wall. Oh, figure 10, sorry. You can see an actual living wall in Seoul, South Korea. This is a trestle design. This isn't used to clean the air, it's more just for aesthetics, but we still like some of the aspects of it. Figure 11 is actually here in the Bronx, a building that has no natural light, which shows an active modular phytoremediation system. Currently, there is no living wall system tailored to the New York City subway environment. We believe our experience in the New York City subway system can be healthier, more comfortable, and more visually pleasing through the creation of an underground living wall system. We have designed a living wall specifically tailored to the New York City subway environment to address air quality, comfort, and beautification. So site selection. We targeted larger transfer stations for our site selection because these stations showed elevated concentrations of particulate matter. For example, stations such as Times Square, Grand Central, and Christopher Street, which showed concentrations that far exceed the EPA 24-hour ambient air standards. These stations also have abundant wall space to maximize the amount of living walls we can install, as well as a higher pedestrian foot traffic to expose to plants.
This is our living wall system diagram. So on the left side, you can see all the factors that we considered in order to design our solution. So we looked into plants, substrate, the structure to support these plants, forced mechanical air, a water system, light, and we also considered the system's operation and maintenance. And we see our living wall bringing these 3 benefits of better quality air, beautification, and comfort. So as you saw in the previous rendering and these diagrams, our living wall system consists of rows of plants. There's 8-inch diameter round pots inserted onto tilted 8-foot-long plastic extrusions with holes. And the plants are staggered per row. Each tilted extrusion is bolted onto the subway wall platform, and the vertical spacing ranges to accommodate different types of plants. Each one of these tilted extrusions will conceal air ducts, hoses with misters, and LED grow lights. And the way the system is designed, the verticality of it and the compact design will avoid overcrowding station platforms. So these are some more detailed drawings of the whole system from different views. In the front elevation, you can see the 8-foot-long rows of plants. The plants are staggered per row to allow for the optimal growth of the plants. And then the air, water, and light systems are concealed. So in the front elevation, you can't see the inner workings of the wall. On the one side of the wall, we have a container where all the duct manifolds, recirculating water pipes, pumps, filters, and other systems are concealed. And also there's a display on this part of the design, which is going to show the performance of the system. Lastly, in the plan view, you can see that we're planning to install some kinetic tiles that are going to generate some of the energy for those systems passively. And in the following slides, we're going to go through each one of these systems in more detail. So we started by researching the right plants. So not all plants are equally good at collecting particulate matter in the subway environment. So we came up with 4 criteria. The first one is leaf structure. So we're looking for plants that are broadleaf. They have wax and wettability, which will help with the adherence of particulate matter. And also we're looking for rich microstructure, for example, trichomes, which is illustrated in that image in the bottom, which will inhibit particulate matter from getting re-entrained once it gets stuck on the leaves of the plants. And then we're looking for plants that need to be watered weekly or bi-weekly, that require little light and low maintenance. So this study shows that plant species selection plays a very important role in particulate matter removal efficiency. 7 different plants were tested, and as you can see, the one that is represented in red, which is the Boston fern, was able to collect more particulate matter than other plants due to its characteristics.
So based on the criteria and characteristics we came up with for selecting plants, we chose English ivy, Boston fern, and spider plant. All of these plants have a high surface area to chemical removal ratio. They thrive in low light, require low maintenance, and they all have air purifying qualities. So our substrate for our design was soil, which effectively breaks down PM through rhizodegradation. In nature, PM is absorbed into the soil from rain and precipitation, as well as when leaves fall onto the ground. Rhizodegradation is the biodegradation of contaminants in the soil by microbes. These microbes break down PM in the soil surrounding the root system of the plant. This creates a net removal of PM from the atmosphere. Our washout system will mimic this natural process.
So subway air holding particulate matter will be funneled into 6 by 2 inch ducts through turbines that are located on the side of the container of the wall, as you can see in the diagrams. And each row of plants will be served by its own individual fan. And the air is going to move in a steady and slow flow in order to avoid the deposition and accumulation of particles within the ductwork. And then small nozzles are going to diffuse air onto each plant. And once the air reaches the end of the row, it will be recirculated back into the container on the side of the wall and mixed with new incoming air. So our system is modular and can be repeated in order to serve different needs for different subway stations. So the length of the wall, or how many times we repeat these 8-foot sections, will be determined by the flow rate, or the amount of particulate matter on the station that we intend to remove, and the height of the wall, or how many shelves, or the distance between the air and the plants, will be determined by the deposition velocity, which, as defined by Stokes' law, is the maximum velocity at which particles break from stream and deposit onto the surface. Our plants will be watered with a light mist on a plant schedule. There will be a pump inside this side container of the wall that will transfer the water to the misters, and there's a mister located above each plant. Besides irrigation, those misters will also act as PM entrainment eliminators and wash the particulate matter off the leaf surface. Also, there's a trough located under all of these plants to catch water dripping from the surface of the living wall, or the plant leaves, and that water is also going to be recirculated. Lastly, the water draining from the pots will be recirculated, so it will return back into that container, will be filtered, and then pumped up again to irrigate the system.
So our design will incorporate LED grow lights. They'll give up a white light to fit into safety regulations of public spaces. LED lights require low energy. They'll be in a time schedule to mimic night and day to give plants a chance to rest and new saplings a chance to grow. So our design will be partially powered passively by kinetic tiles. Kinetic tiles generate electricity when compressed by walking by converting kinetic energy into electricity. This will help powering our LED lights, fans, and misters. Tiles are made from recycled rubber, which further enhances the sustainability of the design. Maintenance is very important to this project. It will include pruning, replanting, repositioning of plants within the living wall, and fertilizing the soil. The irrigation system will need to be inspected regularly to ensure proper water flow and water sludge buildup from PM is clean. We will also need to ensure mechanical maintenance such as replacing light bulbs, as well as regularly inspecting the forced air and kinetic tiles.
By installing a display of air monitoring data on our living wall, we wanted to highlight the importance of making reliable, hyperlocal, and real-time air monitoring data available to the public. The health effects of poor air quality are particularly pronounced in low-income communities and communities of color due to historic discrimination in access to housing and racist land use planning that places polluting infrastructures in these neighborhoods. So these communities rely on the MTA and the subway daily for their transportation, and local stations are disproportionately affected by poor air quality. Currently, the federal approach to air quality monitoring is problematic because there's limited fixed monitoring locations that don't necessarily measure point concentrations that are very high and may impact people's health. New York State has secured $3 million in funding for a new air monitoring initiative that intends to give communities access to this data in hopes that it will inspire a more direct relationship between their needs and mitigation strategies. So our future work will focus on a comparative life cycle assessment and cost analysis of the system. Ideally, we would want to compare our proposal to a conventional filtered mechanical ventilation system. More research needs to be done on sustainable materials, for example, recycled concrete, plastic, steel, and ceramic or clay aggregate. More studies need to be done on the electrical power for the operation of the mechanical system watering and lighting needs. Also, other passive strategies besides the kinetic tiles could be explored. And we need to gain better understanding of how often these plants need to be replaced.
Imagine walking through a subway environment with a lush vertical garden, fresh air, earthy smells, cool and calm, a place to relax while waiting for the next train. Living walls for the New York City subway system. Thank you.